Hi there. Welcome to Chapter 2.3 from Stevens' Matrices, Vectors, and 3D Math, a game programming approach with MATLAB. Alright, in this chapter, we're going to discuss the dot product. It is my favorite operation in 3D Math. Now, we actually already covered this in Chapter 1, where we defined a dot product between two vectors, and that helped us solve systems of equations or perform transformations of various types. Here we're going to use the dot product again, only now we're going to use it to do some operations in 2 and 3D in terms of trig. We're actually going to do some trig without doing any trig, and that's what makes the dot product so wonderful. So let me define it at first, right here. So U dot V, and it looks like a times sign, but it's not. It's actually the dot product sign. You should be familiar with that from Chapter 1. And suppose I have vectors in 3 space, so they each have 3 terms. So this is the vector U, this is the vector V. So the dot product is the product of the first 2 plus the product of the second 2 plus the product of the third 2. So that's what this is right here. So it's a nice, simple algebra. It's nothing but multiplication and addition. And what you should notice, as we did back in Chapter 1, you take these 2 vectors, when you do the dot product, you actually get a scalar, a single number. That's why it is often called the scalar product. Okay, and so the dot product as defined here is exactly the same as it was in Chapter 1, and it satisfies all the properties that we covered in Chapter 1. For example, the dot product distributes across vector addition. It's also worth noting that if you take the dot product of a vector with itself, that is actually just the size of the vector squared, right? And you can tell that because if you look at the size of the vector, that's this part right here, and then you square it, that 2, what happens is the square root goes away and you're just left with the interior. But that's just the dot product of any vector with itself. It's the first 2, product of the first 2, plus the product of the second 2, plus the product of the third 2. Right? Okay, so here's where we bring in the trig, the beautiful part of the dot product, is that it can be defined equivalently like this. U dot V can also be defined as the size of U times the size of V times the cosine of the angle between them. And you think about this, anytime you have 2 vectors, whether they're in a plane or in 2D or in 3D, if you put their originating points adjacent to each or on top of each other, it actually forms a plane, right? And in there is an angle between those 2 vectors, whether that's 2D or 3D. The 2 vectors form a plane, and there is an angle between them. And this angle here that we're talking about, we'll assume it's between 0 and 180 degrees, or pi, right? In other words, if I have 2 vectors U and V like this, then the angle we're talking about is this angle, right? Okay, so between any 2 vectors is an angle, and you can define the dot product of the 2 vectors in terms of the angle between them and their lengths. And this equivalent relation, because it's still valid that this is also still the definition. This is just an equivalent definition, right? So to prove that equivalence, basically what we're going to do is use the law of cosines, right? Let me put that up here. I'll erase some of this. It's getting kind of sloppy. Okay, most of it's gone. All right, so if you look at our triangle here and apply the law of cosines, and we'll say this is our angle of concern. And what the law of cosine says is that this length squared plus this length squared minus 2 times the size times this length times this length. It's right over here. Sorry, I'm going over it. Times the cosine of theta is equal to this length over here squared. Right? So that's just the law of cosines. And proving that's actually not trivial. You got to drop a perpendicular, but it's a well-known law. And so all we're going to do is simplify some stuff. We're going to note that if you take u minus v, the length of that squared, that's the same thing as taking the dot product of u minus v and itself. And now if we take the dot product of u minus v times itself and perform the properties of distribution across addition and subtraction, what you get is the same FOIL multiplication that you do with polynomials, right? So it's going to be the first, the u times u, then the negative u times v, another negative u times v, and then a plus v squared. So I get this row here. But u dot u is just the size of u squared. V dot v is just the size of v squared. Right? And so what I'm going to do is I'm going to take this size of u squared, gets rid of that one up there. This size of v squared gets rid of that one right there. I'll divide by negative 2 on both sides. That leads me to this line. And then, oh, actually I still have the negative 2. Now I divide both sides by negative 2. And I get u dot v is the size of u times the size of v times the cosine of theta. This is very handy. Now I can also solve this equation for cosine theta. And what that reveals, just dividing size u, size v on both sides, is that the cosine of the angle between these two vectors can be determined algebraically. In other words, without any trig, right? So if you take u, dot it with v, divided by the product of their sizes, of their lengths, you get the cosine of the angle between them. And that turns out to be very, very handy. And then you can actually get the angle between them, but there you do need some trig. There you do need to use the arc cosine. So if you take the arc cosine of this element here, this quotient, then you'll wind up with the actual angle. And that angle again will be given between 0 and pi. In other words, like this. If the vectors meet in an angle like that, then it will basically be the angle between them that is less than 180. In other words, you'll never get this angle back, basically the way the arc cosine function works, right? Okay. In other words, if your two vectors look like this, it will not return this angle greater than pi. Okay. All right, so let's do a couple of examples. We're going to determine the cosine of the angle and the angle between the two given vectors. So I have this in 2D. We'll start with 2D. And basically, to get the cosine of the angle between them, I take u dot v over size u size v. And let's see, u dot v is just going to be 1 minus 6, so that gives me the negative 5. The size of u is just the square root of 1 plus 9, so it's the square root of 10. The size of v is just the square root of 1 plus 4, so it's the square root of 5. I do a little simplifying, and I get negative root 2 over 2. All right, and that one you might actually know, right? You don't necessarily need the arc cosine function. If you look at negative root 2 over 2, we are going to be over here on the 45 from the negative x-axis. So this is actually going to be 135 degrees, or 3 pi over 4. Again, you can also do that if you have your calculator with the arc cosine. And it's worth noting, and I think I passed this up, if you're doing this on a calculator or software, on a calculator it's often denoted cos inverse, right? And in MATLAB it is denoted acos for arc cosine. So only in text is it actually written out as arc cosine. Maybe in some software, I don't know. But cos inverse if you're using it like a TI, and a cos if you're using MATLAB. Okay, so, and again, if you do arc cosine of this value, it will return, because everything's in radians in software, it will return this number only expressed as a decimal. All right. And you can convert that to degrees, and then it might look more familiar to you. Okay, so if we're in 3 space, 2 vectors in 3 space, the cosine of the angle between them is just the dot product of these 2 vectors. So it's going to be 1 times -1, which is -1, plus 2 times 3, which is 6, plus 3 times 5, which is 15. So you -1 plus 6 plus 15 gives you 20. Divide by the size of u, which is 1 plus 4 plus 9. Then you take the square root. You get the square root of 14. And the size of v is 1 plus 9 plus 25. Take the square root. And this one is not one of the few that are known, so you really have to use software or a calculator. And when you take the arc cosine of this, you get 0.443, right? But that's radians, so if you multiply that by 180 over pi, you'll get 25.4 degrees. Another useful property of this formula, so let me show you this formula here. I'll rewrite it here. The cosine of theta equals u dot v size of u times the size of v. So notice the only way that this thing equals 0 is if u dot v equals 0. And when the cosine, if the cosine of theta equals 0, right, then that means the angle between the 2 vectors right there is either pi over 2, negative pi over 2. But so in any case, they're orthogonal vectors, right? When I say orthogonal, what I mean, I'm not sure if we discussed orthogonal in chapter 1 or not, but 2 vectors are called orthogonal if the angle between them is pi over 2, 90 degrees. In other words, perpendicular, right? And generally, when we're talking about vectors, we use the word orthogonal instead of perpendicular. But I will often use perpendicular anyway. Right? So we can actually use this as a definition. 2 vectors are orthogonal or perpendicular if their dot product is 0. Right? And it goes the other way around. If their dot product is 0, then the 2 vectors are orthogonal. So if you wanted to prove that these 2 vectors are orthogonal or perpendicular, all you do is get the dot product. So you have 2, let's see, plus 4 minus 6. And that gives you 0. So these 2 vectors, if you were to sketch them out in 3 space, would be perpendicular, or what we will now call orthogonal. All right? And there's another use of this identity. Right? And I'm going to write it down here again. Cosine of the angle between the 2 vectors is just the dot product of the 2 vectors over the size of the first times the size of the second. And there is no first or second. The order actually doesn't matter. So notice the sign of this is entirely determined. Right? When I say the sign, I mean plus or minus. The sign of this is entirely determined by u dot v. Right? So if u dot v is less than 0, that means the cosine of theta is less than 0. Right? And so that means the angle between them is bigger than pi over 2. In other words, it's an obtuse angle. Right? So if you take u dot v and it's less than 0, that's bigger than 90 degrees. If you take u dot v and get 0, and this is what we just did in the previous page, that means the angle between them is 0. I'm sorry, the cosine of the angle between them is 0. And the actual angle between them is pi over 2, or 90 degrees. In other words, they are perpendicular, or orthogonal. And if u dot v is positive, right, then that means the cosine of the angle between them is positive, which means the angle is between 0 and pi over 2, or less than 90. In other words, it is an acute angle, right? So that's pretty handy. So now we can tell whether the angle between two vectors is a right angle, or if it's obtuse or acute, just by looking at the sign of the dot product, right? Absolutely no trig involved, and that's user-friendly, especially if you're using a machine to do these calculations. A couple other ones. The cosine of the angle, if I look at u dot v over the size of u times the size of v, remember that's the cosine of the angle. It's an important formula, that's why I keep writing it down. If this is -1, then the vectors are in opposite direction, right? The angle between them is pi, or 180 degrees. If that u dot v over size u size v is equal to 1, then the angle between the two vectors is actually 0, and they're collinear, pointing in the same direction, right? Okay, so let's do a couple of examples here, and then we'll do one very important application. Example 1. Determine if the angle between this vector and this vector is acute, obtuse, or a right angle. All I have to do is take the dot product. 1 times 3 plus -11 times 55 is -52. Since that is less than 0, the angle is obtuse. Determine if the points A, B, and C are collinear. What I'm going to do, if I have A, B, and C, I'll just look at, and I'll label them A, B, C. I'll look at AB, right? I'll look at AC. And we've done this in previous sections, and we're just going to see if AB and AC are parallel. Well, specifically, if you look up here, that means the cosine of the angle between them is -1 or 1. In other words, all we have to do is look at this and see if it's -1 or 1. All right? So I take AB, gives me this vector. AC gives me this vector, and that's just subtracting term by term. All right? 3 minus 1, -4 minus 2, 13 minus 5 gives me 2, -6, 8. And doing the same thing with A and C gives me AC. Okay, and we'll let theta be the angle between them. I'm just going to look at u dot v over size u size v. And when I take their dot product, it's going to be 2 times -1 plus -6 times 3 plus 8 times -4. That's going to give me -52 if you kept track of that, which I didn't, so I'm going to assume that it's correct. And then you divide by the size of u, size of v. That's going to be the square root of 4 plus 36 plus 64. Square root of v is going to be, or the size of v is going to be the square root of 1 plus 9 plus 16. So there's our sizes. Do a little simplifying. It actually turns out to be -1. Because that's -1, I know that my points actually don't look like this. They look like this. A, B, C. All right. Actually, A, B, if you look at it, A, B, and AC point in opposite directions. but they are in the same line. Right? Okay. And then the final application, this is going to be a two-part video because this is getting kind of long. The final application, this is very important to, especially game programmers, I guess. Suppose I have a ball that's flying towards a wall, right? There it goes. This is the ball position in various times, right? So it's going down this way. And I want to know, when has it crossed the wall, or when did it hit the wall? And sometimes it will cross it, but suppose I want to know when it goes past some line. Well, this is really easy. I can do this without any trig or calculating distances between points and lines. What I can do is I just take any normal vector to my wall, right? However, and I get some point from which on the wall, and I look at some normal vector, any normal vector. The point could be over here and there. It could actually be on, as long as the wall was to continue, it could be like that. I just need a point and a normal vector. And then what you do is all you have to do is, this angle theta, right? I can get that, the cosine of theta equals u dot v over size of u times the size of v. And basically, remember, if u dot v is less than 0, the angle is obtuse. And if u dot v is greater than 0, it's acute. So all I'm going to do is I'm going to figure out this normal vector, and I will create the vector, which is really easy just through subtraction, from that same point to where the ball is. We'll assume this thing is a ball, right? And so I'll call that u1. So I'll just look at n, the vector n, dotted with u1. And I'll see, if this picture is correct, then that would be acute, and that would be less than 0. Sorry, it would be greater than 0. Then I take n dot u2, right? And again, that would be greater than 0 because it's acute. And I would continue this every time I get a position on the ball. And then suddenly, and between n dot u3 would be greater than 0, and then n dot u4 would suddenly be less than 0. Right here, there's a switch from acute to obtuse. So if you draw this one, the angle was acute. Suddenly, the angle became obtuse. That means I passed through the right angle. That means I passed through that wall. Right? So it can be very handy. And all of this is done without any trig. And calculating dot products is trivial, right? It's just multiplication and addition. And so you can do this collision detection without any trig. And it's very fast. It's very easy. All right, so this is a long enough video. I'll give you a break, and we will start. We'll finish up this chapter with the next video. All right. See you then. Bye.